So in this class we'll be discussing about Hartley oscillator. So Hartley is the first type of LC oscillator. So you can look at the circuit diagram of Hartley oscillator. As you already know that an oscillator is made up of two sections. The first one is the amplifier section and the next one is a feedback network. So in Hartley oscillator, this section is the amplifier section and this section is the feedback section. So this amplifier is a common emitter amplifier using voltage divider bias. You can see that the emitter end is common, the input is given to the base end and the output is taken at the collector. So we are using a common emitter amplifier as amplifier section in this oscillator, and the feedback network is composed of a tank circuit made up of three reactive elements Z1, Z2 and Z3. So as I already told you, in Hartley oscillator, Z1 will be an inductance, Z2 will also be an inductance and Z3 will be a capacitance. Now if you want the oscillator to work, what you have to do is, first thing we have to provide the DC voltage, that is VCC. So when we apply this DC voltage to the active device that is used in amplifier configuration, there will be a small amount of noise in the active device due to the flow of charge carriers. The small amount of noise at the output of the amplifier is given to terminal 2, that is it is going into the tank circuit, and this signal is again passed on into the amplifier section. So this keeps on going and we'll be able to get oscillations in this particular circuit. Now whenever we want to get sustained oscillations, we have to satisfy the Bark-Cousin criteria. The first criteria is that the total phase shift inside the circuit should be always 360 degrees. So we'll see how we are getting 360-degree phase shift inside this circuit. This is a common emitter amplifier voltage divider bias. This common emitter amplifier, when we give an input at the base, the output will be out of phase by 180 degrees. So this amplifier is providing a phase shift of 180 degrees. So as I told you before, when I give a positive going input, the output will be a negative going. So because this is a negative going in, terminal 2 will be at negative voltage, terminal 3 is at ground level, that is 0. So automatically terminal 1 will be at positive voltage. So between terminal 1 and terminal 2, that is terminal 1 and terminal 2, you'll be having a phase shift of 180 degrees. So here a phase shift of 180 degrees and here a phase shift of 180 degrees. So totally you'll be getting a phase shift of 360 degrees. So the first Bark-Cousin criteria is satisfied. Next we have to make sure that the product of A and beta should be equal to 1. Now what we'll do is that we'll be finding out the condition for beta so that we will be able to make the value of A beta equal to 1 so that we are able to get sustained oscillations. So now we'll be finding the frequency of oscillation of Hartley oscillator, and that is called as analysis of Hartley oscillator. To find the frequency of oscillation of Hartley oscillator, we'll be using the general form of LC oscillator. This is the equation that we derived in the last class, and we know that the equation of general form of LC oscillator is given as HIE into Z1 plus Z2 plus Z3 plus Z1 into Z2 into 1 plus HFE plus Z1 into Z3 is equal to 0. So this is a general form of LC oscillator. Now what we'll do is that we'll substitute the values of Z1, Z2 and Z3 in this equation to find the frequency of oscillation for Hartley oscillator. Now for Hartley oscillator, we already know that Z1, Z2 and Z3, Z1 is inductance, Z2 is also inductance and Z3 is a capacitance. So if we write the inductive reactance of L1, I can write this one as Z1 is equal to J omega L1 plus J omega M. This M is the mutual inductance of this inductor. Similarly, I can write the value of L2 as J omega L2 plus J omega M, and the capacitive reactance as 1 by J omega C. So this is the equation. Z1 is inductive reactance. It is J omega L1 plus J omega M. Z2 is a inductive reactance. So it is given by J omega L2 plus J omega M. These two m values are nothing but the mutual inductance of the inductor. Z3 is capacitive reactance and it is given as 1 by j omega c. So now we've got these three values, Z1, Z2 and Z3. All these values has to be substituted in equation number 1. So I'm going to substitute all the values in equation 2 in equation number 1. So if I substitute, I can write this value as, so I'll be getting HIE. The value of Z1 is this. So I'll be getting j omega L1 plus j omega M plus the next value is Z2. Therefore, I use this value. So it becomes j omega L2 plus j omega M plus Z3. So therefore Z3 value is 1 by j omega c. So I'll be writing it as plus 1 by j omega c. Just substitute the values of Z1, Z2, Z3 in this equation. So next I'll be getting plus Z1. So Z1 value is j omega L1 plus j omega M into Z2. So Z2 value is j omega L2 plus j omega M into 1 plus HFE plus Z1 into Z3. So Z1 value is over here, j omega L1 plus j omega M into 1 divided by j omega c is equal to 0. So what we do is we simplify the equation. So in this first part, what we do is we take j omega outside. You can see that j omega, j omega, j omega, j omega is there, and here we've got 1 by j omega c. So this entire equation, what we'll do is that we'll take j omega outside. So in this first term, if we take j omega outside, I'll be getting it as j omega HIE into L1 plus M plus L2 plus M plus, if I take j omega outside from the numerator, then I have to divide the denominator by j omega. Therefore, I'll be getting it as 1 by j squared omega squared c. Plus, so if you take these two terms, here you've got j omega common and here also you've got j omega common. So if we take j omega common outside, I'll be having j omega into L1 plus M. And here if I take j omega outside, j omega into L2 plus M. And this term comes as it is, so it is 1 plus HFE. So in the last third term, you can see that you've got j omega common over here. So I've taken out j omega, so it is j omega into L1 plus M. In this term, we've got j omega in the denominator. So what we do is we take j omega outside. So if we take j omega outside as a numerator, I have to divide the denominator by j omega. So here I'll be getting it as 1 by j squared omega squared c. So now this entire equation becomes equal to 0. Now again simplifying. So this equation, the first part, so it is j omega HIE L1. I'm just rearranging. So L2 comes over here. This M and M added together, you'll be getting 2M. And this 1 by j squared can be written as minus. So I'm writing it as minus 1 by omega squared c. And here if you can see, we've got j omega over here and j omega over here. So multiplying these two j omega, you'll be getting j squared omega squared. So j squared is minus 1. So you can write these two value, the product of these two values as minus omega squared. So it is minus omega squared L1 plus M, L2 plus M over here as it is, and then 1 plus HFE. Again coming to the last term, that is the third term, we've got two j omega terms. So when we multiply these two terms, I'll be getting j squared omega squared. The value of j squared is minus 1. So I'm writing it as minus omega squared. This term comes as it is, so L1 plus M. And here, this 1 by j squared, I can write it as minus 1 by omega squared c. That is equal to 0. So this entire term, what we do is that I'll take the second term and third term. So if you look or observe closely at the second and the third term, you can see that the first term, that is minus omega squared L1 plus M, and this minus omega squared L1 plus L1 plus M is common. So these two terms are common. So you can take out this term from term 2 and term 3. So that is what is happening over here. So this term comes as it is, there's no change over here. So I write this term as it is. So it is j omega HIE into L1 plus L2 plus 2M minus 1 by omega squared c, minus you take out omega squared L1 plus M in these two terms. So if I take this term outside, I'll be getting the remaining terms. So here I'll be having L2 plus M into 1 plus HFE minus. So if I take omega squared L1 plus M outside, that is if I take minus omega squared L1 plus M outside, I'll be getting it as minus 1 by omega squared C. This is equal to 0. Now this is the main equation, and from this equation I'll be able to find the frequency of oscillation of Hartley oscillator and the condition for sustained oscillation. So if you want to find these two terms, you have to take this equation and you have to find the two parts. You have to merge the two parts. One is you have to get the imaginary part and the other one is a real part. Using the imaginary part, you can find the frequency of oscillation, and using the real part, you can find the condition for sustained oscillation. So using this equation, the imaginary part can be used to find the condition or the frequency of oscillation, and the real part can be used to find the condition for sustained oscillation. To find the frequency of oscillation, we have to equate the imaginary part to 0. So the imaginary part in equation 3 is made equal to 0. The imaginary part in equation 3 is omega HIE L1 plus L2 plus 2M minus 1 by omega squared C is equal to 0. So if this term comes to my right hand side, I can just neglect this entire term. So I have just this term. So I'll be getting L1 plus L2 plus 2M minus 1 by omega squared C is equal to 0. We already know what is the value of omega is, and omega is equal to 2 pi f. And because we are going to assume or we are going to find the frequency of oscillation, we call this omega value as omega naught. So we take it as omega naught and the frequency as f naught. So we write this equation as omega naught equal to 2 pi f naught. We just substitute the value of omega naught in this equation. So if I write this equation in terms of omega naught, I rewrite this equation. So I'll be getting L1 plus L2 plus 2M, that is equal to, so this term comes to my right hand side. Because I've got a minus sign over here, I'll be getting it as plus 1 by omega naught squared C. And if I substitute the value of omega naught as 2 pi f naught, I'll be getting the value on my right hand side as 1 by 2 pi f naught the whole square into C. So because you need to find the frequency of oscillation, you keep the value of 2 pi f naught to the numerator part and then you bring the other terms to the denominator. Just rearrange the equation so that you can find the value of frequency of oscillation. So what I've done is I've brought this value to my left hand side and this value is brought down to the right hand side denominator. So if this is interchanged, you'll be getting 2 pi f naught squared, that is equal to 1 by, this comes to the right hand side denominator, so I'll be getting L1 plus L2 plus 2M into C. And as I have to find the frequency of oscillation, we remove the square term, so therefore on the right hand side we'll be having a square root. Therefore I'll be getting it as 1 divided by square root of L1 plus L2 plus 2M into C. So you have this extra term of 2 pi. So if you want to find the frequency of oscillation, you just bring this 2 pi to your right hand side. So if I bring this term to my right hand side, I'll be getting the final answer of frequency of oscillation. So I can write the frequency of oscillation as 1 by 2 pi into root of L1 plus L2 plus 2M into C. So this equation is called as a frequency of oscillation, and for simplification what we do is that we rewrite this equation as 1 by 2 pi square root of L equivalent into C, and the value of L equivalent is nothing but this entire equation, that is L1 plus L2 plus 2M, and this is called as a frequency of oscillation of Hartley oscillator. Next, in order to find the condition for sustained oscillation, we equate the real part of equation 3 to 0. So this is a real part of equation 3. So the value is omega squared into L1 plus M into L2 plus M into 1 plus HFE minus 1 by omega squared C. This is equal to 0. So this term, if you bring it on the right hand side, it becomes 0. We can neglect this first term. So this term alone will be equal to 0. So I can write this equation as L2 plus M into 1 plus HFE minus 1 by omega squared C is equal to 0. So as before, because we've got this negative sign, we bring this term to the right hand side. So I can just rewrite this equation as L2 plus M into 1 plus HFE. So this term goes to the right hand side, therefore it is 1 divided by omega naught squared C. So as before, we write the value of omega naught as 2 pi f naught squared. So I rewrite this omega naught as 2 pi f naught. So here if you can see, the left hand side term remains the same, and the right hand side term I've just changed the value of omega naught as 2 pi f naught. So this becomes 2 pi f naught the whole square. So what we do is, because it is square term, we substitute the value of f naught. So now this equation becomes 1 divided by, this 2 pi becomes 4 pi squared, and this f naught value was found, and we substitute the value of f naught squared. So if we square the value of frequency of oscillation for the Hartley oscillator, we'll be getting it as 1 divided by 4 pi squared. The square root term is removed. So I'll be getting L1 plus L2 plus 2m into C. And here we've got another C because of this term. So this C and this C, both terms will get cancelled. And similarly the 4 pi squared and the 4 pi squared will get cancelled. So this term of 1 divided by L1 plus L2 plus 2m can be brought up to the numerator. So I can write the equation as L2 plus m into 1 plus HFE, that is equal to L1 plus L2 plus 2m. So this is your equation. Now we again simplify the equation, and here if we want to find the condition for sustained oscillation, we'll be able to get sustained oscillation only if we limit the gain of our amplifier. So the gain value denotes that it is nothing but HFE. So what we're going to do is that we're going to find the value of HFE. HFE is nothing but the gain of common emitter amplifier. So if we find the gain value of common emitter amplifier, and if we know the condition for that, we'll be able to get sustained oscillation. Now rearranging this equation, we bring this term L2 plus m to the right hand side. So we'll be getting the equation as 1 plus HFE is equal to L1 plus L2 plus 2m divided by L2 plus m. And we take this 1 also to the right hand side. So we'll be getting it as minus 1. So if we take the common LCM, we can see that we'll be getting the term in the numerator as L1 plus L2 plus 2m minus L2 plus m. So this L2 and L2 will get cancelled. So this is a bracket, and 2m and m will get cancelled. So we'll be getting the answer as L1 plus m divided by L2 plus m. So this is the solution for sustained oscillation in Hartley oscillator, and this is the value for HFE.